This work is largely based on a paper that we put out last year and a paper that's shortly going to appear. So, okay, great. Let's get started. So, the broad motivation for this talk is to understand the ADS-CFT map. Okay, the ADS-CFT map is a map between a gravitational theory on the one hand and a purely quantum mechanical system without gravity. But the sort of question that we want to address is, can we derive something like, can we give something like a derivation of this map? Or equivalently, if I give you a suitable quantum system, then how do I go about finding gravity within its Hilbert space? Okay, of course that's a big question, and I don't know. We won't even begin to answer it. But a somewhat related but more concrete question is the following. When does the time evolution of a state in a quantum mechanical system admit a semi-classical description? Okay, and I emphasize the word time evolution. It's not just about one state, it's about the time evolution trajectory of a state. Okay. Now in ADS, the reason this question is relevant is that in ADS-CFT, we know that the quantum time evolution of some states in the CFT admits a dual gravitational description at large n in terms of classical geometries. Okay. So at least in some sense, the time evolution of these states is classical. But this classical description emerges in a completely different set of non-trivial variables, namely the gravitational variables. And it would be nice to have a systematic way to identify these dual gravitational variables or these dual classical variables when they exist. And this is somehow this would be at least some progress towards understanding the ADS-CFT map. So in this talk, we are going to take inspiration from some work in the theory of quantum information and computation. In particular, there is this thing called the Gottesman-Neal theorem. I'll tell you more about it as we go along. But roughly speaking, they ask the following question. This theorem addresses the following question. When can a quantum circuit be simulated efficiently on a classical computer? Okay, so this is their version of asking the question, when can a quantum time evolution be classical? So from their point of view, a quantum time evolution is classical when the circuit can be simulated efficiently on a classical computer, and this theorem addresses when that can happen. And interestingly, the answer to this question uses a discrete version of what we all call the Wigner function in quantum mechanics. So before we go on, let me just give you a brief reminder of what the Wigner function is. Okay. Now in standard quantum mechanics, particle moving on a line in some potential, the Wigner function is a quasi-probability distribution in phase space. Forget the word quasi for now. Think of it as some attempt at representing a quantum state as a phase space distribution. Okay. So this is the standard formula that you all have probably seen. Given a state psi, one attempts to write down something like a phase space distribution, something that depends on Q and P, corresponding to that quantum state. And if you want, here's another way of rewriting the same formula as the one-point function of some operator. This operator a hat is sometimes called a phase point operator. It's basically the Fourier transform of what we usually call a displacement operator, this thing in blue here. And very roughly, you can think of this Fourier transform as giving you an operator which is delta function localized at the point q comma p. But something that treats both Q and P on the same footing as opposed to, yeah, go on. Hat just means operators. So A hat is an operator, Q hat is an operator, P hat is an operator, everything else is not an operator, and you insert that into the one-point function. Okay, very good. This Wigner function, as I was saying, kind of looks like a probability distribution. It has all the nice properties that you want. First of all, it's real. It integrates, normalized, it integrates to 1. And if you integrate it only over the p direction or only over the q direction, then you get the probability distribution in the other direction. Okay, so that sort of marginalizes this distribution. But however, it is not a probability distribution, which was the reason I said quasi. And the reason it's not a probability distribution is because it's not everywhere positive. Okay, at some points q and p, this thing can become negative. Okay. Now, states for which the Wigner function is everywhere positive may be regarded as classical states. Okay? Indeed, there are states for which W is everywhere positive. A standard example of this is a Gaussian state. In fact, you can show that for a pure state, a pure state will have a positive everywhere non-negative Wigner function. When I say positive, I really mean everywhere non-negative. A pure state will have an everywhere non-negative Wigner function if and only if it is Gaussian. Okay? And of course, we think of Gaussian states as being classical. So at least for pure states, and in this setting of L2 of R, you can think of positivity of the Wigner function as being equivalent to Gaussianity, or being the state being classical. Okay. Now, so far we've only discussed this case of L2 of R, particle moving on a line. But it turns out, it turns out from all this literature in the theory of quantum information that you can also define Wigner functions for finite dimensional Hilbert spaces. Okay. So the way these people do this is that if you have a Hilbert space of some dimension capital D, I will always use capital D to denote the Hilbert space dimension in the rest of this talk, then you take a phase space, a discrete phase space, which is basically the lattice ZD times ZD. It's basically a set of D squared points. Okay. And one tries to represent any quantum state in this Hilbert space as a distribution on the set of D squared points. Okay. Now, this formalism works best when D is prime, but it can be generalized to other D. And if this is not a very important catch, but for things to make best sense, we just simply choose D to be prime. Okay, it's not too important though. Okay, so the way you go about defining this Wigner function is that you first make a choice of an ordered orthonormal basis. So orthonormal basis is of course clear, but by ordering I mean that there's a zeroth vector, there's a first vector, there's a second vector, and so on. Okay, so there's an ordered orthonormal choice of basis for the Hilbert space. And then with respect to that choice of basis, you define what you might think of as the exponentiated version of the translation operator and the exponentiated version of a momentum operator. So sometimes these are called clock and shift operators. You might have seen them before. But basically think of this Z hat of P as being, the operator e to the I P times Q hat, something that is an exponentiated position operator. And think of X hat as being e to the I Q times P hat. Okay? An exponentiated momentum operator, or a translation operator, as you can see from this expression. So once you have these exponentiated translation and position momentum and position operators, you then define the Wigner function in direct analogy with the previous case. Okay. So this is the definition of the Wigner function in the discrete case. You'll hopefully recognize the analogy or the similarity with the formula, with this formula here, in the standard quantum mechanics case. Okay, the analogy runs much deeper. I'm just showing you this at the level of the formula, but literally you can in fact even write this phase point operator in terms of the corresponding displacement operators that you build out of Z hat and X hat in the same way. Okay, so at least roughly you can see that this object is constructed in the same way that you might have constructed it in the continuum case. Okay, so there you have it. That is the definition of the Wigner function in the finite dimensional setting, and it satisfies all of the nice properties that the continuous Wigner function satisfies. In particular, it's real. It is normalized. If you sum it over the entire phase space, so to say, it sums to 1. And if you sum the Wigner function only over P or only over Q, then you get the corresponding probability density in the other variable. Okay. All right. But as before, the Wigner function, even in this case, is not a probability distribution. And I think you will not be surprised if I tell you that the reason it's not is that it can take on negative values. Okay. Now here comes the Gottesman-Neal theorem. As we discussed before, states with everywhere positive or non-negative Wigner functions you might think of as being classical, and the Gottesman-Neal theorem makes this very concrete. within this finite dimensional setting, their statement is as follows. Any quantum circuit which starts with a Wigner positive state, namely a state with an everywhere non-negative Wigner function, and only uses positivity preserving operations. So there's a class of quantum operations which do not spoil this positivity property of the Wigner function. These are sometimes called stabilizer operations. So the statement is that any quantum circuit which starts with a Wigner positive state and only involves positivity preserving operations can be efficiently simulated on a classical computer.
Sorry,
yes.
Do you mind?
Yes.
Really sorry.
Yes.
But if you took, say, 2 qubits,
yes.
And you looked at a bell pair,
yes.
That presumably is a state where the Wigner function is negative somewhere or the other. Can I relate that fact, with the negativity?
You're trying to ask whether negativity is related to entanglement in some way?
Yeah, that would be the intuitive.
I think that there is some relationship like that. In fact, I think states which in a setting with multiple qubits, you can show that you can only violate Bell's inequalities if you have some Wigner negativity. Yeah, but essentially because states which are Wigner positive can be thought of as having an underlying hidden variable description in terms of the Wigner function.
Exactly.
It's essentially a phase-space description.
Yeah, so that ties Bell's theorem.
That's right. So there is there's a statement like that. I'm not going to discuss it, but it certainly exists. Yeah.
So just to understand this statement of the theorem, so if I have a quantum circuit and I have
yes.
entangling gates, that is not sufficient to conclude that it cannot be simulated on a classical computer.
That's correct. Yes. Yes, that's correct. And that's a well-known fact actually in the theory of stabilizer computation. That is why stabilizer circuits work so well. They're essentially classical in the sense that they can be efficiently simulated classically, but they still create highly entangled states. Okay. All right. So that is some statement about how Wigner positive states are, or in what sense Wigner positive states are classical. But for a more general state, the Wigner function, as I said, need not be everywhere positive or everywhere non-negative. It will have some amount of negativity. So one can try and quantify how negative the Wigner function of a state is. And here is one measure that I'm going to use through the rest of this talk. So I'm going to call this thing the Wigner negativity. It's sometimes called mana in the literature. The definition is that you just take the absolute value of the Wigner function and sum it over phase space. Okay. Now, of course, if this guy was everywhere non-negative, the absolute value here is irrelevant, and the sum would give you 1. Okay. You can take a log of this thing if you want to set it to 0, but I'm not going to do that. If at any point in phase space the Wigner function is negative, then this guy will be greater than 1. Okay. So effectively, what I am interested in is understanding how this thing differs from 1. This thing is always, oops. This thing is always greater than 1, and the question is how much greater than 1. Okay, yes. So far I'm talking about finite dimensions. So in the continuum case, you might be tempted to integrate this thing over the absolute value of the Wigner function. That looks okay to me, but I'm afraid in some cases that quantity might diverge because of the infinite volume of phase space. So I'm not sure what people think of or use as the best measure in the continuum setting. But in this talk, I will just restrict to discrete setting throughout. Yeah.
So apart from understanding whether it's positive or negative,
Yes.
there is no bound on the magnitude.
The individual.
Let's say in this discrete case, given the Q,
Yes.
this Wigner function, how positive can it be? How negative can it be?
Individually. There might be. I'm not sure. Actually, that's a good question.
If you add them, they will give 1.
That's right.
And if you add the magnitudes, it will be greater.
Greater than 1. It's actually upper bounded. The sum is upper bounded by square root of the dimension of the Hilbert space. You can pretty easily show that this thing is always upper bounded by square root of the dimension of the Hilbert space. But square root of the dimension of the Hilbert space is a very large number, right? It's an exponentially large number. Yeah. Very good. Now, so this thing over here, the negativity of the Wigner function, you can think of as some measure of how non-classical a state is. Okay, it's a measure of some measure of the intrinsic quantumness of the state, if you like. Then there are several ways you can think about that. First of all, it decreases monotonically under stabilizer operations. So if you perform a classical operation, this thing cannot increase. Okay, this is how people in quantum information theory often quantify various things. They are monotones. Okay, the Gottesman-Neal theorem or its generalizations state that this quantity is a good measure of the complexity of simulating the quantum circuit on a classical computer. Okay, this is a slight generalization of the statement I gave you before. And yes.
What did you say under stabilizer operation? Every non-classical will lead to classical monotonality, right? That's what you said.
No, what I said was if you take a state with some negativity and you act on it with some stabilizer quantum operations, then its negativity cannot increase. Okay, because you're doing something classical, so that better not increase the negativity, and indeed that is the case. So this quantity is what people call a stabilizer monotone. Yes.
The stabilizer operation was defined as one which, when given a Wigner function that is positive, keeps it positive.
Exactly. You can give a more detailed definition, but I'm not going into the details. Yeah. Yes. Yes, so as Sandeep said, you can think of these as operations which act on Wigner positive states and map them to Wigner positive states. Okay. Let me give you another characterization. There are these things called displacement operators. Okay, you can define displacement operators even in the discrete setting. Stabilizer operations are ones which map displacement operators to other displacement operators. Okay. You can think of this as, roughly speaking, rotations and translations in phase space. Okay. But okay, if you want, we can talk in more detail after the talk. All right. Great. So you can think of this quantity as some measure of the complexity of simulating this circuit on a classical computer. And in fact, it's also this Wigner negativity is also related to quantum uncertainty. Yes. Yes.
Even if I add a classical thing, just the number of dimensions of the Hilbert space increasing will increase the complexity, I assume.
So I'm always working in a setting where the dimension of the Hilbert space is fixed, but you want to increase the dimension of the Hilbert space?
Yes, so shouldn't you look at the quantity which is scaled with the dimension?
If you're in a setting where maybe the dimension can change, like if you're in an evaporating black hole or something, where you're collecting more and more radiation, maybe in that setting you have to be a little creative in how you define it. I'm always working in a setting where you have a fixed dimension, you have a qubit, d-dimensional Hilbert space, and that's it. All the dynamics will happen within a fixed Hilbert space. Okay, very good. So this Wigner negativity, there's another, just to say, there's another aspect of Wigner negativity which you can think of as a measure of an intrinsic quantumness, namely the statement that Wigner negativity is related to uncertainty. Okay. So for instance, consider the probability distribution in Q. Okay, so Q was your ordered orthonormal basis that you picked. You can of course compute the probability distribution of the state psi in this basis, and here's that classical probability distribution. Corresponding to this classical probability distribution, you can associate an entropy. You can of course associate whatever measure of entropy you want, but here I look at what you might call as the half-Renyi entropy. Okay, this thing here is the half-Renyi entropy of that classical probability distribution. Okay, you can show that this half-Renyi entropy of the probability distribution in Q is always lower bounded by the log of the negativity. Okay, so if the negativity is 1, namely the state is Wigner positive, the right hand side is 0, this inequality is trivial. But if you have a non-trivially Wigner negative state, then the right hand side is positive, and that tells you that this distribution has to have some spread. Okay, now I gave you this inequality in Q, but it turns out that this inequality is more generally true. For instance, the minimum of S half of Q comma S half of P is also lower bounded by the negativity. And in fact, if you look in any direction in phase space, okay, then the minimum over all such directions in phase space of the half-Renyi entropy is lower bounded by the negativity, the log of the negativity. Okay, so that tells you that this negativity necessarily implies some amount of quantum spreading in phase space. Okay, so if you can from this point of view, you can think of this object as some measure of the quantum spreading of the state in phase space. The reason I say all this is because this bound will become important later in the talk. All right, so now after all that, how much time do I have? Maybe I have 20, 25 minutes? Yeah. 350, so, okay, 25 minutes, okay, great. So after all this, this introduction, now let me come back to the main question that I started the talk with, okay? When does the time evolution of a state in a quantum system admit a semi-classical description? This was the question. Now, inspired by these results that we just mentioned from the theory of quantum information, we may say that this happens when the Wigner negativity of the state remains in some sense small all along time evolution, right? However, recall that the Wigner function is defined with respect to an ordered basis. Okay, you start with the choice of an ordered basis, and then you define the Wigner function with respect to that choice of ordered basis. So then the question becomes, if I give you an initial state psi naught and some time evolution operator, namely some Hamiltonian, can we find an ordered basis for the Hilbert space such that the Wigner negativity growth of the state under time evolution in some sense is small or is minimized? Okay. If we could do that, then you would end up showing that somehow the state seems to remain classical through its time evolution. Okay? Yes. Yes, tell me. Yeah, what?
So what is the statement there? So
The statement?
Yeah, so it's a statement about the basis, or?
Yes. This is a statement about the basis. So I told you that the Wigner function and Wigner negativity are defined with respect to a choice of ordered basis, right? Now the question is, the state and its time evolution may look very Wigner negative in one basis, but maybe there's some other basis where it looks kind of not so negative, right? So really what you would want to do is you would want to look over all possible choices of ordered basis and say, okay, there exists one where the negativity is as small as possible. That's roughly what you.
Can it also change depending? I think it can change depending on psi naught also.
Yes. So the problem has two inputs: the initial state psi naught and the time evolution operator h, and then the output would be you give me a Wigner function representation in some basis such that the negativity looks small.
And when that happens, you would say that the system is classical.
Yes, in this basis. Yes. Meaning what I would really say is that this is the right choice of variables to look at the time evolution such that it looks kind of classical. Okay, so the first claim is that the early time Wigner negativity growth is indeed minimized by a particular choice of basis, and this basis is called the Krylov basis. Okay? So what do I mean? So okay, before I tell you what that statement means, let me just quickly review what the Krylov basis is. So the Krylov basis is a very simple construction. You're given some initial state psi naught. From psi naught, you can of course build h psi naught and h squared psi naught and so on. And then what you do is, of course, the problem with this set of states is that they are not mutually orthogonal, so you just orthogonalize them. Okay. So psi naught, h psi naught minus the overlap with the zero guy, and so on. Just Gram-Schmidt these. Yes.
The point is that the basis you pick is dependent on get psi naught, I think.
Correct. So your input is psi naught and the time evolution operator, and you get to pick whatever basis you want, such that this whole trajectory looks classical. That's right. And exactly as you point out, this basis that I constructed depends on psi naught and the Hamiltonian. Right. Okay. So this basis, which by the way, in order for these set of states to form a basis, psi naught has to be sufficiently generic with respect to the Hamiltonian. For instance, if psi naught was an energy eigenstate, you would not get anything, right? You would just get one vector. Okay, but if you imagine that H is a sufficiently chaotic Hamiltonian and psi naught is a sufficiently generic vector without any symmetries and so on, then indeed it's not easy to convince yourself that this will form a basis for the Hilbert space. Okay, so that's that is called the Krylov basis. And now, what do I mean when I say that the Krylov basis minimizes the early time negativity growth? Well, we mean the following. Now, at t equals 0, you have the state psi naught, right? It's a very simple calculation to show that if I just chose psi naught as my 0th basis vector, then it will have 0 negativity. Okay, this is like a one-line calculation from the definition of the Wigner negativity. So, if that is the case, I might as well take psi naught as my first vector, right? Choose psi naught as the first basis vector. Okay. Now, the next thing that I'm allowed to vary over is the first basis vector. What should I choose as my first basis vector? At this point, you can show that the coefficient of the linear in time growth, namely the order t term in the negativity, is always larger for any basis other than the Krylov basis. Okay, so if you want to minimize the coefficient of the order t term in the negativity, you're forced to pick the first basis vector as the first basis vector of the Krylov basis. Had you picked any other vector, the coefficient of the order t term would have been larger. Okay, and then you keep going.
So this is
Yes.
true for any h and
It is true for yes, that's correct. Up to this generic condition. That's right. Yes.
So wouldn't you somehow but also have some prejudice about, maybe the initial state itself somehow being classical?
Yeah, maybe.
Yeah, in the sense that if you could possibly take some generic state in the Hilbert space, like the complexity saturating state or something. And then if you're constructing this, you would still miss on somehow some useful notions of classicality.
Maybe. So if in particular, if you had some operator algebra and you wanted to realize, have a state where the operator algebra is realized classically or something, maybe. I mean, there could be other things you can build on top of this, for sure. And that's actually something that I also want to think more about. But in this talk, we will not do that. Okay. But that's a great comment.
Just to add to that,
Yeah.
you're not using the dimensionality of the Hilbert space being large anyway.
It will come. It will
But
come.
if once you start doing that, you might have
Yes.
a notion coupled to large.
Yes. It will come. The large dimensionality will come. Yeah. Very good. Excellent points. Yeah. So just to wrap up this part of the discussion, what I was saying was that you can just continue with this argument. So the first basis vector you're forced to pick to be the one in the Krylov basis. Then you can show that if you have a choice of basis where you agree with Krylov basis up to the mth basis vector, but it differs at order m plus 1, then the coefficient of the order t to the m plus 1 term in the negativity would be larger for any other choice of basis vector other than that of the Krylov basis. Okay, so that's what one means by the statement that the negativity is minimized. The negativity growth is minimized by the Krylov basis. Okay, is that clear? Okay, great. Now, of course, this was a sort of perturbative analysis. It was sort of looking at the negativity growth in perturbation theory in time. But we would like to say something more. We would like to say something about the finite time behavior of Wigner negativity. And here, in order to make progress, we will resort to using tools from random matrix theory, because otherwise these calculations are pretty hard. Okay. So what we will do is we will now take this Hamiltonian to be a d by d Hermitian random matrix. In this talk, I will resort to using the Gaussian unitary ensemble, but I expect many of these results will generalize to other unitary ensembles. And chaotic systems are expected to show random matrix theory behavior. So I would expect much of what we say here to apply to chaotic systems. Okay. As I was just saying, the initial state must also be sufficiently generic with respect to the Hamiltonian. So for instance, in the basis where the Hamiltonian is a random matrix, you can simply take the initial state to be the first basis vector, the vector 1, 0, 0, 0, 0, because since the Hamiltonian is random in that basis, this vector is generic with respect to the Hamiltonian. So the next claim is that the Wigner negativity with respect to any generic basis, so if you just pick your basis generically without fine-tuning it, then the Wigner negativity with respect to any such generic basis will grow very, very rapidly within an order 1 amount of time evolution and saturate to its maximum value. The maximum value happens to be close to square root of d. Okay, so this I'm showing you here a numerical plot of the negativities. So the orange curve is the negativity calculated with respect to the basis in which the Hamiltonian is a random matrix. Okay, and the blue curve here is the negativity calculated with respect to the Krylov basis. Okay, so at least numerically you can see that in a generic basis the negativity almost rapidly, almost instantaneously shoots up and becomes exponentially large. In the Krylov basis it seems to grow gradually for a while and then at a very late time saturates to this same value. In fact, what we are going to show is that in a generic basis this saturation happens at an order 1 time, whereas in the Krylov basis there is a power law growth for a long time and then the saturation happens at an exponential time. Okay, so in that sense we will argue that the Krylov basis does exponentially better than a generic basis. Okay, so this was a numerical plot. We will now give analytical arguments for this behavior.
Sir,
Yes.
when you say negative Mr. basic fact, so what does it mean about whether the system is classical or quantum? If I look at the growth of Wigner negativity.
Yes. So what I mean by that is that if the state at any point has an order 1 amount of negativity, I think of it as being classical or semi-classical. But if the negativity is very large, or in particular scaling with square root of d in this case, then I would think of that as a very quantum state.
So this plot would suggest that if I choose the Krylov basis to
Yes.
look at it,
Yes.
its time evolution is still being as a classical.
Correct. It looks semi-classical for a long time. That's right. Whereas in a generic basis, it almost instantaneously becomes non-classical, seemingly.
And the Krylov basis is known to kind of know the spread of the wave function.
Yes.
Kind of thing which you also
Yes.
cited.
Yes.
So is this two things?
I suspect so because, as I told you, the negativity lower bounds the spread, right? So if a state has a very large negativity, then it will also have a large spread. Yeah.
That was the uncertain.
That was the uncertain. Yeah, exactly. That's right. But in some sense, the negativity is a more covariant object because it lower bounds the spread in any direction in phase space, not just in Q, in one direction. Yeah. Okay, very good. So in the next 15 minutes, I'm going to try and justify these assertions analytically. So first, let's talk about the negativity in a generic basis. So in the generic basis case, we can simply take the basis to be the one with respect to which the Hamiltonian is a random matrix. Okay, because H is a random matrix, your basis is generic. And recall also from our previous slide that the first state will be the 0th vector, the first vector, if you like, in this basis. Okay. So now we would like to calculate this object. We would like to calculate the negativity of the state as a function of time, namely this state over here. But because calculating it for one Hamiltonian out of this ensemble is a difficult thing, what is easier is to calculate the average of that. The average of that over the whole ensemble. Okay. So this thing is easier to calculate. So the way we will do that is by using a couple of tricks. So the first trick is as follows. Consider a change of basis, consider a change of basis which leaves the initial state psi naught invariant, but rotates the rest of the basis vectors by some hard random unitary u sub ij. Okay. At this point, this is just a trick. It's a convenient one. Okay. Now, so this is the definition of the Wigner function. So what you're going to do is, for all vectors k comma l, which are not the initial vector, you're going to rotate them by some unitary. Okay. But the point is that this unitary does not act on psi naught. So imagine that there's a u and a u dagger sitting here and here. But you can always put that same unitary on this side and that side for free because it doesn't act on psi naught, right? So effectively what has happened is that both of these time evolution operators have gotten conjugated by the same unitary. And since I'm averaging over GUE, which is unitarily invariant, this rotation does nothing, right? So such a change of basis will not affect the negativity, okay? Now, because such a change of basis does not affect the negativity, I might as well do that change of basis and integrate over it, okay? So you might think that I'm crazy, I'm complicating my life for no reason, but just one more line. What I've done is I've calculated this negativity in some rotated basis, where this u is the rotation, the unitary rotation, and then I've just integrated over all such unitary rotations with the Haar measure. And I just argued for you that when this thing sits inside this H integral, this object is u invariant, so this integral does nothing. Okay? But now, what is convenient, the way this works, the reason this helps is that you can exchange these two integrations. Okay? So instead of doing the H integration first, you do the u integration first. Okay? And the point is that you can do the u integral, the Haar integral, by using standard tricks from the theory of Haar integration. Okay? Yeah.
Right? Even for time, explicitly time dependent unitary will work, right?
Yes, that's right. As long as the ensemble is unitary invariant. Okay? Now, one difficulty with doing this calculation is that you want to calculate the Haar integral over something which involves an absolute value. Okay, that's a bit of a pain because the absolute value is not analytic, but you can get around that by using another trick, namely the replica trick. Okay, so you basically calculate the Haar integral of w to the power 2n, and then for every integer n, and then analytically continue n to half. That's the standard replica trick, adopted in this case to the calculation of the absolute value of the Wigner function. And this calculation can be done by using standard tricks from the theory of Haar integration. And you can actually analytically continue in n equals half, and this is the formula you get. Okay, you get a very explicit formula for the negativity, the average value of the negativity, in terms of this function which I'm calling S. You can think of this S as the average survival probability, namely the probability for the Hamiltonian to take psi naught to psi naught. And this thing, by the way, is in GUE, for instance, is also closely related to what we call the spectral form factor. Okay, it's very, very closely related to that. In fact, it's the same thing, actually. The average value is the same thing. Now, in this formula, you note this factor of square root of d. Okay? The spectral form factor, or the survival probability, it starts off at 1. It starts off its life as at 1. So this term is not there. Okay, and this thing is almost 1. But in any unitary ensemble, in particular in GUE, this spectral form factor decays away from 1 in an order 1 amount of time evolution. In just order 1 amount of time, it will decay away from 1. The moment that decays away from 1, this factor grows to something proportional to square root of t. Okay? So that tells you that in an order 1 amount of time evolution, the negativity will become exponentially large. Start scaling with square root of d. And in fact, that's the analytic formula almost exactly matches the numerical one. The red curve is the analytic formula. The blue dots are the numerical ones. Prediction up to order 1 by square root d corrections. So this was done at d equals 100 or something like that. Up to order 1 by square root of d corrections, our analytic formula reproduces the numerical calculation. Okay? Very good. So this was the first assertion, namely that in a generic basis, the negativity grows to an exponentially large value in an order 1 amount of time evolution. The next assertion is that in the Krylov basis, the negativity grows much slower. Okay, so you can see this on a log-log plot. It shows a power law growth for a long time, and then so this region here is the power law growth. The x-axis is scaled with respect to square root of d. So up to times of almost close to of order square root of d, The negativity shows a power law growth. And then exactly at times of order square root of d, it shoots up and saturates to the same large value. Okay? What is happening is that the fine tuning that you've done in terms of choosing your basis is helping you keep the state classical for a long time, for almost exponential time. But at that point, you lose all the degrees, the fine tuning you had. Okay, the state has become sufficiently random that the fine tuning that you did was useless, and you lose all of that, and the negativity jumps up. I have 5 minutes. Okay, great. Okay, so this is just a pretty plot to show you how the Wigner function evolves in time, not too important, but we can understand the slow growth of negativity in the Krylov basis analytically. This goes as follows. The Krylov basis has the special property that it tridiagonalizes the Hamiltonian. So if you express the Hamiltonian in the Krylov basis, it has this form. It only has the first diagonal, these ANs, and the first off diagonals, these BNs, and everything else is 0. Okay, these A's and B's are called the Langchos coefficients. It turns out that you can calculate the average values of these Langchos coefficients in GUE. Okay, for n fixed, n being this label on these ANs and BNs, for n fixed and d going to infinity, this AN average value is 0 and the BN average value is 1. Okay. Note the limit. The limit is send d to infinity holding n fixed. So you're looking at some block of the matrix up here, where n's are not scaling with d. Okay. So at least in this part of the Hilbert space, for fixed n as d goes to infinity, this Hamiltonian looks very simple. Okay, in this basis, this is the effective Hamiltonian, if you like. This is the effective Hamiltonian, if you like, in this limit, in the d going to infinity limit. This Hamiltonian is very easy to diagonalize. This is the spectrum. If you don't recognize this cos theta is basically the Wigner semicircle. It's basically related to that Wigner, the fact that GUE has a Wigner semicircle distribution for its energy density. And using this effective Hamiltonian or this effective description, you can calculate the wave functions at time t. Okay, the time evolution of the initial state. They are given by some very simple functions. This is what happens to them. They spread in n up to some point up to n of order 2 times t, and then they exponentially decay. That has to do with this Bessel function. Okay. So the wave function is only spread up to some point n of order 2t, and then it's almost 0 outside. It's exponentially suppressed outside.
Just show the previous.
Yes. Yes.
So for 0 to n.
Yes.
N was what?
N was the label for this basis vector. So now I'm denoting these basis vectors in the Krylov basis by the index n, the integer n. Okay. Of course, this approximation, what we did here is we approximated this Hamiltonian in this particular way, right, where d was sent to infinity holding n fixed. This approximation only makes sense, if these exponential tails don't become important at n's of order square or n's of order d, and you can estimate when that happens, and that happens roughly at times of order square root of d. Okay, that's why this square root of d was important in terms of time.
So when you say that AN and BN are 0 and 1,
Yes,
on an average, that average is over the
ensemble, over the GUE ensemble. Yeah. Okay, so the last point is to argue that the negativity grows as a power law in the Krylov basis, and now it's almost obvious. Recall from this discussion of uncertainty that the log negativity gives you a lower bound on the half Renyi entropy of the probability distribution in Q. You can turn that around and view it this way. The half Renyi entropy of the probability distribution in Q gives you an upper bound on the log negativity. Okay, But I told you that this wave function is only spread out over a region up to n equals 2t and has 0 support outside. Okay, when that happens, this thing is spread out only over some box, right? So when that happens, the half Renyi entropy is upper bounded. In fact, you can pretty easily argue that it's upper bounded by square root of t. The square root of t you can think of as what would have happened if it was just uniformly spread out over a box of size 2t. Okay, it's not, but it's still upper bounded by square root of t. Okay, and since this half Renyi entropy is upper bounded by square root of t, up to this factor of 2, you can see pretty easily from this expression that the negativity can grow at most as t. Okay, the growth of the negativity can't be faster than t. Actually, one can do better than that. You can use a slightly finer argument using Jensen's inequality to show that the negativity growth is bounded by square root of t, not t. But either way, it's a power law in time. Okay. So what that means is that the negativity cannot become exponentially large in an order 1 amount of time evolution, or indeed for any finite amount of time evolution. For it to become exponentially large, you have to wait for an exponentially large amount of time. Okay, and that's what we see in the numerics. Numerically, the power that we see here is about 0.42, which famously is less than half. Okay, less than half. Yes. Okay, very good. So let me conclude. I think I've run out of time. Let me conclude. So we've argued that in the Krylov basis, time evolution looks as classical as possible or as semi-classical as possible at sub-exponential times. The Krylov basis is therefore well suited for a semi-classical effective description at such times, at sub-exponential times. And it is tempting to propose that this effective description that one came up with is akin to gravity. Okay? Or more specifically, gravity around a particular background. This seems to be true at least in the double scale SYK model, what people sometimes call Q-deformed JT gravity. In that model, the Krylov basis states in the UV indeed become the geometric states, namely the chord length or the fixed wormhole length states of the gravitational theory. And our hope is that this is a general principle underlying the ADS-CFT correspondence, which can guide our search for gravity in more general quantum systems. Thank you. Yes?
So I'm just curious, so do you think that this generic element in the Krylov basis would be similar to a coherent state or would be still different?
Coherent state. What do you mean by a coherent state?
Generally, I mean, coherent state is...
No, I know what a coherent state is in L2 of our quantum mechanics.
I just mean from the point of view of the fact that it mostly looks like classical.
Yes.
From that
I would say that this Krylov basis, so I think of, if you're looking for a gravitational analogy, I think of the Krylov basis states as fixed length states. So in the gravity path integral, you can insert fixed length states in the bulk. Namely, if you try to calculate, yeah, go on.
I see. Yeah.
Yes. So you can calculate, for instance, the Hartle-Hawking wave function in fixed length basis, as Sandeep was doing this morning, right? I think of these states as sort of being analogous to those fixed length states.
I see.
Yeah.
Here
Okay.
you have a fixed dimension, right?
Yes.
And let the dimension tend to infinity.
Yeah, exactly. That's right. Yes. Yeah, I mean, you can make pretty good arguments that it's related to the complexity of simulating a state on a classical computer. So at least it's a measure of that. Namely, if the negativity is large, then it will be harder to simulate that state classically. It may not be a measure of complexity in the sense of circuit complexity, but it's a measure of the complexity of simulating a state on a classical computer. Yes?
Black holes will be more closer to generic states or is Krylov?
Generic states.
These Krylovs are somehow semi-classical, they have lower negativity.
I mean, it seems like the Krylov basis gives you a good,
But if we have
yeah.
a description of black holes, theory of gravity, will it be closer to a generic state or to a Krylov?
Well, the Krylov, so maybe I should say this again. The Krylov basis is basically a basis which is good for describing dynamics around a given background state. So you start with some background state. Yeah. So it's more like you're describing gravitational fluctuations around the black hole. So that's what the Krylov basis is good for in some ways. If you're talking about microstates, then this talk was not about microstates. These are more like the kinds of fluctuations that Sandeep was talking about. These length of the wormhole kind of states. Yeah.
I'm curious about the first part of it.
Yes.
Can we change the ensemble to some other ensemble?
Yes, you can.
The result is.
So this formula that I derived, this formula is completely ensemble independent. The only thing that we actually used was the fact that it was unitarily invariant. So for instance, you could have written the same formula down in the SSS ensemble. Just replace this S with the average value in that ensemble.
So but the Krylov thing is somehow we need a Hamiltonian.
You need a specific Hamiltonian, but the general philosophy is not very different. So what will be different are the specific values of the specific average values. They might be slightly n dependent and so on. But the general point I'm making, namely the fact that it grows as some power law for an exponential time, I think that is true in any ensemble.
So who should one think about this choice of basis from an ADS-CFT point of view?
Well, I'm tempted to say that it's this right bulk basis.
Yeah. But somehow I feel like the psi naught should also be. Should have a class.
That's right. So it's the right bulk basis to choose. It's the right basis to choose where you see the bulk gravitational degrees of freedom around a given background.
So, for instance, these could be fluctuations or something.
Correct. Sorry, Sandeep has been wanting to say something.
Just a follow-up. I mean, you use the Gaussian unitary ensemble, and at least there, if I'm right, you find that the Lankos basis, this negativity grew more slowly up till time of what, a root t?
Yes, that's right.
And then it sort of gone.
That's right.
And sort of similar question, because it seemed that this was related, I mean, these coefficients or whatever related to the double trumpet, the spectral form factor. And the reason where I'm going with this is the following. If you look at the SYK model, as you know, as opposed to the GUE, the spectral form factor behaves very similarly, but the operator growth is much slower in the SYK model.
Okay.
Because there's a notion of simple operators.
Okay.
So do you think this will be true in a wider
SYK. Okay. SYK, I don't know. These statements.
Also chaotic, different sort of.
Yeah. I mean, I think that at least the initial power law growth may be valid, but it may break down at an earlier time or something. It may not be valid till times of order square root of d. It may break down much before that. I haven't thought about that. That's a really great question.
No, but I mean, to the extent it's related, more to the spectral form factor, then it might be more universal.
It may be. It may. But I mean, the Krylov basis arguments were not related to the spectral form factor. What was related to the spectral form factor was this generic basis, the negativity in the generic basis. But even that we used unitary invariance. So I should really not say anything about SYK because SYK doesn't have unitary invariance either. Yeah.
So then
but that's a really great comment. Yeah. Thank you.